Welcome to Two Projects. In this video, we are going to explain about the project that is enhancing cervical cancer classification through a hybrid deep learning approach integrating DenseNe 201 and Inception V3. So before getting into the execution, first let us understand what is this project about. Cervical cancer, which is one of the most common cancers affecting women globally, ranking fourth in prevalence. Each year, around 5,70,000 new cases are reported, and approximately 3,10,000 women lose their lives to this disease. A major reason is for high death rate is that many cases are diagnosed at a large stage when treatment becomes less effective. Early detection is therefore crucial for improving survival rates and patient outcomes. Current manual methods, that is, currently cervical cancer screening largely relies on manual examination of pap smear images. This process is labor intensive, time consuming, and prone to errors. Doctors may interpret the same image differently, overlapping cells can make analysis difficult, and the natural variation in cell shapes and sizes add to the complexity. These challenges makes it hard to achieve consistent and accurate diagnosis, which can delay treatment and reduce the chances of successful recovery. Automated and precise diagnostic methods are needed to address these limitations and also support timely medical decisions. So in recent years, deep learning has become a powerful tool for analyzing medical images because it can automatically learn and extract important features from complex data. This has made it possible to classify diseases like cervical cancer more efficiently than manual methods. Popular methods like PresNet 50, DenseNet 201, Inception V3, and Exception have been successfully used to identify different types of cervical cancer cells, showing that artificial intelligence can play a key role in supporting medical diagnosis. Despite their success, these models still face several limitations. For example, they can overfit when trained on small data sets, meaning they perform well on trained data but poorly on new unseen data. Some models struggle to maintain a good balance between precision, that is, correctly identifying positive cases, and recall, capturing all actual positive cases. Additionally, these architectures often require heavy computational resources and they may find it challenging to extract the most important features from highly complex cell images. These issues emphasize the need for more accurate, reliable, and efficient methods to improve cervical cancer diagnosis and help doctors make better clinical decisions. So to overcome with all such issues, this project it combines two powerful deep learning models that are DenseNet 201 and Inception V3 to improve the accuracy of cervical cancer detection from pap smear images. DenseNet 201 is particularly useful because it efficiently reuses features from earlier layers and helps to prevent the vanishing gradient problem, which make training deep learning networks difficult. On the other hand, Inception V3 is excellent at capturing features at multiple scales, allowing the model to recognize both fine and coarse patterns in the images. To make the most of the both models, the system uses feature fusion approach, which merges the information extracted by DenseNet 201 and Inception V3 into a single rich feature set. This combined representation provides a more complete understanding of the image, helping the system to classify cervical cancer cells more accurately and reliably than using either model alone. And here, when the features from DenseNet and 201, that is DenseNet 201 and Inception V3 are combined, the result is very large and complex set of data, which can slow down the system and make computation less efficient. To solve this, the dimensionality reduction methods like principal component analysis and t-distributed stochastic neighbor embedding model has been used. These techniques reduce the size of the feature set while keeping the most information intact, ensuring the model runs faster without losing anything. That is, without losing accuracy. In addition, the model makes use of fine tuning pre trained weights. This means it takes advantage of networks already trained on large general datasets and then adjusts them specifically for the cervical cancer images. By doing this, the model becomes better at recognizing unique characteristics of cervical cancer cells, leading to more accurate predictions. And performance of these models are evaluated with these scores, that is, accuracy, precision, recall, and F1 scores. These metrics helps in understanding how well the model predicts the correct class and balances between false positives and false negatives and handles class imbalance. To get clear picture of the model performance, visualization tools such as confusion matrix, RC curves, and precision recall plots are used, which show how that is where the model is performing well and where it might be making mistakes. So by combining DenseNet 201 and Inception V3 in a hybrid approach, the system is able to classify cervical cancer cells more reliably and accurately than traditional manual methods or existing automated approaches. So we have also added a detection module as the extension where we will be locating where that cervical cancer is present in a particular cell. Not just only classifying whether the person has cervical cancer or not, we will also be localizing where that cancer cells are. For that, we have used YOLO family, where we will be using different versions of the YOLO. And we have also added GradCam, which is an explainable AI technique to make its predictions more understandable. GradCam, it creates heat maps on the images, highlighting the areas that had the most influence on the model's decisions. This makes users can see exactly which parts of the cell images the model focused on when predicting, making the system reasoning, transparent, easier to trust. And also we have created a web-based interface which is created using Flash framework. So this makes the system easy to use. Through this interface, users can upload cervical cell images and receive predictions from trained models directly. This makes the system more practicable and also accessible for users. And moving on to the implementation, these are the steps followed to implement this project. Let's understand what are these steps. So first, we will be importing all the necessary libraries that are required for this project. Then comes data preparation, where we will be loading the data set and we do classification where we will be checking whether the data set has their respective labels or not, and we will be assigning bounding box annotations for the detection part, and we will be splitting the data set into train and test sets. Coming to visualization, we will be plotting the class label distribution graphs to check the data distribution. And then we display sample labeled images to verify the dataset quality and annotations. Then comes data pre-processing. So here at this stage, the images are resized, normalized, and augmented to create variations that improve the model's ability to generalize. Data augmentation techniques are applied to make the system more robust to the changes that we give as input. Additionally, HOG-based features are extracted to capture important texture details. For YOLO training, a data.yml file is created with the dataset paths and also class names. Two sets of data are maintained, one for classification and the other for detection. And we have trained models that is for both the classification and detection. For classification, we will be evaluating all the models using accuracy, precision, recall, and FN score. And for YOLO models, we will be using mean, average, precision, and recall. And we will be selecting the best performance model and we will be using it for future use. And we have developed front end where users will be able to get registered and log in, and that thing will be stored in the database of SQLite, and users they will be able to give input that will be pre-processed at the image, that is that it will be pre-processed at the backend, it will be fed to the train model, and train model will be displaying the prediction. And moving on to the algorithms used, these are the algorithms used for classification and these are the models used for detection. And to implement this project, basically we need two types of requirements, that are hardware and software. So in hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. And software are application of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let's execute. To execute, we are supposed to open the code folder of the project. So now let's open the code folder of the project. So these are the source code files of the project. Let's understand each of them. How will they be used in this project? This folder is the model folder in which we have algorithm information, and this will be loaded into the project code during runtime of the application. And in this folder, we have the data set that is used. So in this folder, we have dyskeratotic images of cervical cancer. So these are the cervical cancer type that is dyskeratotic. Get back. Similarly, we have coelocytic, that is coelocytotic images of cervical cancer. And here we have metaplastic cervical cancer. And here we have parabasal cervical cancer. And in this, we have superficial intermediate level cervical cancer. So these images are split into train and test folders in the output folder. So images which are in the train folder will be used for training the models, and images which are in the validation folder will be used to evaluate the models. Let's get back. And images which are in this output folder are used for training the models for classifying the cervical cancer. And this is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files which are important for the visual appeal. And the next folder is templates folder. This folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And in this folder, we have test cases that we will be using in the front end. And here in this folder, we have images. So let's open train folder. Here we have two subfolders. One is images and labels. In images, we will be having all types of cervical cancers. And in label folder, we will be having cervical cancer locations in the label format. I mean, in the label folder that is in the text format. So first, let's open images folder. So here, all types of cervical cancers are clubbed together. And object locations, that is the two cancer locations are in this label folder. Let's open this label folder. So this label folder, it contains file annotations, that is image annotations, or we call them as labels for the objects in the corresponding images. Here, each label file, it corresponds to an image file in the image folder. For example, the first file is correspondent to the first image in which we will be having cervical cancer locations. And for the second folder, we will be having second label file. Accordingly, for all the images, we will be having all the label files. And these label files, they follow the YOLO format. Let's open file for sample. So here each line specifies a detected object. Here we have many lines, right? So how many number of lines we have, that many number of locations, that means that many number of cancer detections will be detected in the prediction. So here we have 1, 2, 3, 4, 5, 6. Total we will be having 6 detections in the output. And here these are the bounding box coordinates. Let's close this, get back, and now get back. Similarly, we will be having images and the label folder in valid and also test. So train folder is used to train the models and validation and test folder are used for evaluation. So images in this folder are used for training the detection models. So images which are in this folder will be used to train the models for classification, and images which are in this will be used to train the models for detection. And coming to app.py file, so this .py file, it contains information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And here we have notebook file. Here we have two notebook files, which are Jupyter notebook files. They contain combination of code, graphs, and outputs all in one place, and it allows users to write and execute code in individual cells, making it a popular choice for the data science. And then the last file we have is the signup.db file. This file is a database file which is used to store the user information. And coming to this classification notebook file, here we will be training the models for doing classification. So here we will be writing code for doing detection. So this is all about the code folder. Now let's execute. So copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now open Anaconda prompt. It is open. Give the command, give the space, give the command cd, and then give the space. And then paste the copied path. Click on enter. Here, if you observe, current directory is changed to the code folders path. Now compile app.py file. So give the command python space app.py and then click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. So at this address, application has been hosted. So copy this local link provided by the Flask framework and paste it into any web browser. I've copied the link. I prefer Google Chrome, so I will paste it in that. Paste the link here and click on enter. So this is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. So now click on get started. And then now you need to create the account if you have not created. I have already created, so I will directly sign in. Click on sign in and provide your username and the password. Give your username and the password. Now click on sign in. So we are redirected to classification of the project. This is the classification page of the project. So here you can see try now button, right? If you click on that, we will be redirected to option where we need to upload the images. So click on choose file, open the test cases, open the classification because first we will be doing classification. So click on classification. Here we can upload images from any of these folders. So let's try uploading images from this folder. So select any image of your choice, click on open and now click on upload. So this given image, it will be pre-processed at the backend. It will be fed to the train model and then train model will be giving us a prediction. So just wait for a while and here we got the prediction. So here it is correctly predicting that it has dikeratotic, that is dyskeratotic cervical cancer type it is. This is the uploaded image and this is the GradCAD image. So this GradCam image, it highlights the region of MRI that model considers most important for its prediction. Here, red and yellow color area shows high influence, indicating where the model focused to classify the tumor. It helps to validate the model and supports medical interpretation. Now let's try with some more images. Click on try again. And now click on try now. Click on choose file. Get back. Open this folder. So select any image of your choice. Let's upload this one. And now click on upload image. So here we got the prediction. So here we got coilocytotic cervical cancer is there. So this is the image that we have uploaded and here we have GradCam image and it is predicting that it is coilocytotic cervical cancer it is and it is 99.9% accurate. Now let's try with some other images. Click on choose file. Get back. Let's try with this one. So here we got the prediction that it is predicting metaplastic cervical cancer it is. And this is the image that we have uploaded and this is the area where it is focusing more on to predict the metaplastic cervical cancer. Click on try again. Click on choose file. Get back. Open this folder. Select any image. Click on upload image. So here we got the prediction that it is parabasal cervical cancer and it is 100% confident in predicting the parabasal cervical cancer. And this is the uploaded image and this is the GradCam image. These are the, this is the area where it is focusing on for predicting this parabasal. Okay, click on try again. Click on try now. Click on choose file. And now get back. Let's try with this image. Click on upload image. So here we got the prediction that it is superficial intermediate cervical cancer. And this is the uploaded image and this is the GradCam image. So as of now, we have done classification. Now let's do detection. So under prediction, click on detection. And now click on try now. Click on choose file. Get back. Open detection folder. So you can upload any of these images. Let's select this one and upload it. Here also image will be pre-processed at the backend. It will be fed to the trained YOLO model and then YOLO model will be giving us the detection. So here if you observe there are multiple detections. Here if you observe you can see superficial intermediate cervical cancer has been detected and multiple bounding boxes are drawn around the cancerous cells. So here you can observe, right? Cells have been detected. So when we did classification, it was only just telling which type of cancer it is. That is, which type of cervical cancer. And coming to the detection part, it is highlighting the area where that cancer is present. That is, cancerous cells are present. Now let's try with another images. Get back. Now click on try now. Click on choose file. Let's try with this one. Click on upload. So yeah, here we got the detection. Here if you observe, parabasal cervical cancer has been detected and a green color bounding box is drawn around it and it is labeled as parabasal with the confidence score. Here you can observe confidence score is given to every detection. Now let's try with some more. Click on try now. Click on choose file. Select any image. So let's select this one and now click on upload image. And here we got the detection. So here if you observe, there are two types of cancerous cells detected. One is dyskeratotic and another one is metaplastic. And bounding box is drawn around the cancerous cells. Click on try again. Click on choose file. And now let's try with this one. So here we got the prediction. Here you can observe coilocytotic cancer has been detected. Coilocytotic cervical cancer has been detected. Now let's try with the last image. Click on try on. Click on choose file. Now let's try with this one. So just wait for a while. Here we got the detection. You can observe this keratotic cervical cancer has been detected. In this way, you can do detection also. Now let's check with the graphs. So let's check the graphs of classification. Click on that. So here we have visualization data and performance metrics. The first graph shows the distribution graph. So click on I to view it. Here on x-axis, we have all the models that we have trained and on y-axis, we have the metrics. So this graph, it shows the precision comparison graph. Precision is the metric that is used to evaluate all the classification models. Now close this. So let's view this image. That is ROC curve. This is the ROC curve. Close it. And this is the accuracy score, which is also an evaluation metric. And this is FN score. And here we have recall score. This is the recall score, which is evaluation metric. And here we have precision score. This is the evaluation metric. And then here we have sample outcome graph. Here on x-axis, we have different types of targets. And on y-axis, we have number of images. Here you can observe all the each class count. So here for dyskeratotic, here we have number of samples. Kylototic, we have 825. And for metaplastic, we have 793. Like that, we will be having for all the images. And now we have missed one more graph, that is this graph. So here this shows the distribution of data into train and validation sets. Here on x-axis we have train and validation and on y-axis we have number of images. So in train we have 2427 and in validation we have 1622. So these are used to train the model and these are used to evaluate the model. Close this. Now let's check with the detection. Click on detection. And so here we have detection graphs. This is mean average precision score graph. This is the recall graph and this is the precision score comparison graph. Here, if you observe on x-axis, we have all the metrics. I mean, all the models that we have trained. And on y-axis, we have the score. Now click on sign out. In this page, just by uploading images to the application, if you want classification, it will be classifying which type of cervical cancer it is. And if you want detection, it will highlight the area where cancerous cells are present. So this is all about the project.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.